Okay, welcome to lab number 12, and here we're using the ideal gas law, which you can see at the bottom of the card, to determine the number of moles of air in a balloon that you blow up. So I'm going to demonstrate that. This is a fairly simple experiment. I think I'll use a pink balloon. So you can buy balloons at any, I think I got it at the grocery store, Target, Walmart, any, where you can get balloons, hopefully. So we'll start by just blowing it up. And we want to have a spherical shape for this lab because we're using the formula for the volume of a sphere. Which balloons, if you blow them up fully, it's not quite a sphere. So try to blow it up so it looks like a ball, a globe, a sphere shape. Okay, so it's not going to be perfect. Balloons are not made to be a perfect sphere, but because we're using the formula for a sphere, we want to be kind of close to that. So what we're going to do is, using this equation, the ideal gas law, where pressure in terms of ATM, atmospheres, times volume in terms of liters, equals N, the number of moles, times R, which is our constant, which is equal to 0.08206, and the units are liters ATM over moles Kelvin, times temperature, which of course is in Kelvin. This is the ideal gas law. It allows us to relate all of these four variables to each other using the constant R. So today, we're going to assume standard temperature and standard pressure in the room. So what that means is I'm assuming that the pressure in this room is 1 ATM. That's standard pressure. I'm assuming that the temperature in this room is room temperature, which in Kelvin is 298. R doesn't change, and so I'm just dealing with volume and moles in this equation as our two changing variables. What we're going to do is actually pretty simple. We're just going to find the volume of this balloon, and then using the volume of our balloon, we're going to plug into the formula and find the number of moles of air that must be in our balloon. So you can think ahead if you can guess how many moles this is. It's not too often we think about moles of air and how much space those take up. So you can make yourself a hypothesis ahead of time and guess how many moles of air might be in this balloon. That will be fun. You'll find out if you're right at the end. All right, now to find volume, we're going to use the equation 4/3 pi r cubed. And I'm going to write that in a space where you can see it. The equation for volume of a sphere. For this lab, not every gas we deal with is going to be using this spherical equation by any means, but for a balloon, we're using 4/3 pi r cubed. So what is our variable there? It's r, which is the radius. So we need to know the radius of this spherical object. So what we're going to do is actually just trace our balloon on paper, and that will give us the circumference and the diameter, and then you're going to find the radius from that. So a good scientist always does 3 trials. So what I want you to do, and you can do definitely more than 3 trials if you like, is because our balloon is not a perfect sphere, I want you to measure the balloon from 3 different angles. So first I'm going to trace it like this, then I'll trace it this way, and then I'll choose one more angle to trace that balloon and find the radius the best way that I can to calculate the volume. So that way we'll get a close to accurate reading of the volume of this balloon. So when you're tracing it, the widest part of the balloon is what you want. So put your pen so that it's straight down. Don't angle it in or out. Another reason why it's good to do multiple trials, because it's hard to be perfect. We're humans. Human error exists. So I traced my balloon, and as you can see, it's some kind of spherical, even elliptical shape, really. But I'm going now take the diameter, and actually you can find, using this shape, you could get two radius measurements, one the long way and one the short way, and you could average those two as samples. So why don't we do 6? Why don't we do 6 samples total? We can measure the balloon 3 times, and for each one, measure it in 2 directions. So I'm going to measure it on the x-axis and the y-axis. So first I'm going to measure straight across the widest part of the balloon. And that's exactly right on the dot 19. So I'm going to, the proper way to read a ruler, you want 2 decimal places. So it looks really 18.91 is what I'll say for my diameter. And actually, I'm going to show these measurements on a different camera so you can see them up close. So now we've just seen the process for measuring the circumference of a balloon on a piece of paper. And I want to show you measuring the diameter. So here's our balloon. We just measured this. I measured it 3 times. And we're going to take 2 diameter measurements from each of those 3 circles that we drew. So my first one was 18.91 centimeters. I'll be checking that you have 2 decimal places. So make sure that you estimate properly. We've been getting practice with this since the beginning of the semester. So I'm looking for you to estimate to the 100th place. Because our ruler breaks our measurements down to the 10th place, you can estimate out one more to the 100th. That's what I'm looking for. Okay, so if you have a diameter of 18.91, that means your radius is that number divided by 2. And we'll fill that in a second. And I do want you to take 2 measurements from each of the spheres. So I'm just going to turn my paper and take a measurement of the circle in the other direction because it's not a perfect sphere like I was saying. And you want to do it from the widest point so that it represents the diameter the best way that you can. Okay, so this looks like, if I'm going to take a reading and estimate, I would say 16.14. It's between the 0.1 and the 0.2. So I'm going to say the diameter in this direction is 16.14 centimeters, which would mean the radius is that divided by 2. Okay, so let's get those radius measurements. This one is 8.07 centimeters. And our first radius we measured was 9.455. Let's 9.46. We're rounding to keep 2 decimal places. Okay, so we have our 2 radius measurements. We're going to use that in our average, and then we'll calculate the volume of the balloon. So I did measure the balloon 3 times, and I've got our circles here to work with. So measuring at the widest point first, you can see it's a little bit oblong, and that's why it's good to take 2 measurements for this, because it's not a perfect sphere. Okay, and I'm going to say we have 18.62. That's what I'll say, because it's between the 0.6 and the 0.7. Okay, which makes our radius, if we just divide that by 2, 9.31. And let's measure the radius in the other direction. Lining up 0 with one end, and then taking our reading from the other end. 16.5, 16.50 I would say. So it looks like it's right on the 5. It's not more, it's not less. So 16.50. Which makes our radius 8.25 if we divide that by 2. Alright, so we have 2 other radius measurements to average into our final answer here now. And I'll show you the third balloon I measured. The third, it's the same balloon, remember it's the same balloon from 3 different angles. So I measured it once the long way, once the tall way, and then once at some sort of other angle to get a good average, a good representation of this volume. Okay, now this one is looking like 17.05, let's say that. Now obviously, you can see how the circle was drawn. The size of the circle will depend on the size of the balloon, of course, but also make sure when you're measuring it, your pen is straight up and down, it's not angled in, measuring the very bottom of the balloon, and it's not angled out, making the balloon look wider than it is. There's a lot of room for human error there, so being specific to the 100th place is really just practice for you in using a ruler, because the ruler you can estimate to that specific precision level. However, this measurement as a whole, being the sample that we're working with, is going to have some human error associated with it regardless. Okay, just a side note. So diameter, when we divide that by 2, we have 18.53. Notice I rounded up to keep 2 decimal places. Oops, sorry, 8.53 is our radius. And we'll measure it in the other direction as well. So we're going to look and see where that lines up. This is good practice for you to watch some measurements. 16.11, I might guess. It's between the 16.1 and 16.2 marks. So diameter, 16.11 centimeters, which means the radius, about half of that. You can always think ahead. About half of 16 is going to be 8. 8.055 will round up to 6. 8.06 is our radius. Okay, so let's get all of our radius measurements and put them in one place. And then we're going to average them together and use them in the formula for the sphere. Now I've created a table for myself to fill out. You can set this up however you like. But with our 6 measurements we took for radius, we're going to find the average radius, and that goes right into the equation 4/3 pi r cubed for the volume of our sphere. And that volume is going to be used here in our ideal gas law to calculate the number of moles in the balloon. And that's our final destination. So let's look at our different, these T's represent trial, the different radius measurements that we found. So 8.06 was 1 centimeters. 8.53. If we notice that they're all fairly close to one another, that's a good thing. It means our reproducibility was good. 8.25. We have 9.31. That's a bigger one. 9.46. You can see that's the balloon at its most elliptical shape. And then 8.07. Now if you remember, which definitely it should be second nature to you now, how to find an average, we're just adding up all 6 of our measurements and then dividing by the number of measurements we took, which was 6. So first let's add up all of our measurements. Okay, we have 8.06 plus 8.53. I like to hit the equals sign frequently so that I'm sure I'm on the right track and nothing went wrong with me typing into the calculator. Plus 8.25 plus 9.31 plus 9.46, making sense so far, plus 8.07. right? That's a reasonable sum. We're adding 6 numbers just under 10, and we're getting a number about 50. So 51.68, that makes sense. Always think about your numbers if they make sense or not. So we're going to divide by 6. That's our number of samples. We get 8.61. And that is our average radius. And we can use that directly in our equation for the volume of a sphere. Now let's see how we're going to do that. This equation may be looking challenging to you, but let's just break it down. How are we going to start it? Well, r cubed, how about that? So we can just multiply r, 8.61, by itself 3 times. That's easy. 8.61 times 8.61 equals, times 8.61. There we have 638.277. We're going to round up to 0.28. 638.277. Actually, since we're multiplying, we're going to keep our lowest number of significant figures, which is 3. 8.61. We have 3 significant figures. So we're going to keep our measurement with 3 significant figures. 1, 2, 3. The 2 is not above 5, so we keep it here. 638 is r cubed. So now our formula can be written as 4/3 pi times 638. Okay? Now what is pi? What is the value of pi? It's about 3.14, and we can just use that. So we're going to multiply 4/3 times 3.14 times 638. Now we've got numbers to deal with rather than symbols. 638 times 3.14. And if you don't know how to enter a fraction into your calculator, just do times 4 divided by 3. That's what I'm going to do. Times 4 divided by 3. So we have 2,671. And there's some decimal place measurements as well. But we want to keep 3 significant figures. That's these 3. The 1 is less than 5, so we're going to keep it at 7. 2670 with no decimal after it. And that is cubic centimeters. Okay, so cubic centimeters, if you remember, is equal to a milliliter. We're going to have to convert that to liters eventually. But just to remind you about when you have a significant figure situation like this, where your measurement is actually 4 digits long, you're talking about thousands, and you want to keep 3 significant figures. Don't just write 267, because that's 10 times smaller than we're talking about. We're still talking about the same measurement, 2,600 something. So you need to keep a 0 there as a placeholder. But we're not putting a decimal there, indicating we're only being specific to the first 3 significant figures. Okay. Now, let's look at converting this to liters, because we ultimately need liters in our volume equation. Let's just do that right here. We have 2670 cubic centimeters, which, if we remember, cubic centimeters is equal to a milliliter. And we can show that by saying it's a 1-to-1 ratio. Now, how do we convert milliliters to liters? That also should be second nature to you by now. Sorry, milliliters. I'm going to rewrite that. I'll write it up here. 2670 milliliters. And there are 1,000 milliliters in a liter. Milliliters cancel. And we end up doing what? Multiplying by 1,000 or dividing by 1,000? Yes, we are dividing by 1,000. So basically, we just move the decimal place back 3 spots. Or you can put it in your calculator if you need to. So that's 2.670 liters. Now, this 0, if we keep it and it's after the decimal, it's considered significant. It's considered a measured 0. But we only need to keep 3 significant figures. So if we want to be specific about our significant figures, we can write 2.67 liters. It doesn't change the size at all. It just changes the precision. We're only precise to 3 significant figures. So now this, 267 liters, that's what finally goes in our equation for volume, and we can calculate moles. Let's do that. Okay. So our pressure, let's look at PV equals nRT. Our pressure, like we said, is standard pressure. We're using 1 atm. Our volume is what we just calculated, which was 2.67 liters. Liters is the unit. That should go in the parentheses. N is what we're looking for. R is 0.08206. Liters times atm over moles times Kelvin. That's what allows us to relate all those variables. And then we have 298 Kelvin as our room temperature. So let's solve this. 1 times 2.67 is easy. 2.67 liters times atm. Just putting the units together. Now we can do these two numbers together, 0.08206. Sorry, that's 0.08206 times 298. Equals 24.45. So we do N 24.45, and let's see if any units cancel here. This Kelvin, it goes along with the units that are in the numerator, so Kelvins will cancel. So it's going to be liters atm over moles. Okay. Now if we're solving for N, don't worry about the units. The units are not variables. Sometimes people get confused. They think they have to fill something in for each of these units. But we're working with these two numbers. So if it simplifies it, you can just write the numbers. I'm keeping units here for now to show you how they cancel out. Okay, so we're solving for N. We want to put N on a side by itself. So that means we have to take 2.67 and divide by 24.45. Liters times atm over 24.45 liters times atm over moles. So when the moles are on the bottom of a fraction in the denominator, that actually ends up on top. So now let's look at what cancels. Liters, atm. So we end up with the unit of moles. That's great because N represents moles. We're on the right track. We know we did that right. So 2.67 over 24.45. And we get 0.109 moles. Okay, and I kept 3 significant figures because this has 3 and that has 4. We go with the fewest. And that is your final answer. So you have about 1/10 of a mole of air in this balloon. 1/10 of a mole of air is how much you blew into this balloon. And that's how we can use our ideal gas law to calculate certain characteristics of a system that we're dealing with. In this case, we found moles. So, any questions that you have, feel free to use the discussion boards, the Ask the Class, the discussion board for this lab as well, and course messages. And good luck.